start for the last lecture. I know you had a long day and a long week, but I mean, I encourage again, a lot of questions as in the last days were really great. Right, I want to talk about measurements. Yeah? So that's an interesting topic in its own right, and I will also connect it to what we learned in the last day, namely a kind of extended variant of this Keldysh path integral approach, which builds on multiple replicas of the state in the later stages of the lecture. But to begin with, I want to just introduce you to the physics of measurements in many body systems. But to really begin with, measurements is on quantum system is something that you're probably familiar with from small quantum systems. That's what we really learn or teach in the quantum mechanics lecture. And one thing you should be aware, there is two fundamentally distinct types of quantum dynamics, quantum evolution. The one is deterministic in its generator. It is the Schrödinger evolution, generated by a unitary operator here. And the second fundamental ingredient of quantum mechanical dynamics is probabilistic, and it comes due to the interception of the deterministic Schrödinger dynamics by a measurement process. And what happens in a measurement process, it's one of the postulates of quantum mechanics, when you want to measure observable M, represented by a Hermitian operator, which I can spectrally decompose in this way, so write it as a sum of projectors, and the coefficients are the eigenvalues of this operator. Then what happens in the measurement process is that the system suddenly gets projected on one of the eigenstates of this measurement operator. And the probabilistic nature of this process can be read from downstairs here. So this absolute value here is referred to as the Born probability for collapsing into this state. Yeah? So it's determined by the overlap of the projector onto that state with the current state. So this thing here is realized actually as this is lambda psi and this thing absolute squared, yeah? And that is really the probability for the overlap of the state onto which collapse with the current wave function. Okay, so an interesting observation that you can already make in very small quantum systems is that the dynamics that results from the simultaneous presence of Hamiltonian evolution on measurements is that it will never stop, never come to an end in the moment that the Hamiltonian operator, a Hermitian operator, and this Hermitian observable do not commute. Because then whenever I collapse, say, by a measurement into a state, then the Hamiltonian will kick me out again, simply because they do not share a full set of eigenstates. Yeah? So that's this non-commuting nature of operators. And this non-commuting feature of operators is something that you can be familiar with when you think about phase transitions, in particular quantum phase transitions in many body systems. Yeah? So there as well, we have a structure of two non-commuting operators. In that case, they are the two pieces that sum up coherently in a Hamiltonian operator. So the situation for a quantum phase transition, just to remind you, is this. Yeah, we have two non-commuting Hamiltonians. Each of these Hamiltonians by itself stabilizes a state with different physical properties. For example, they are distinct in their symmetry breaking patterns. And an example that you can think of here is this famous Mott insulator to a superfluid transition that you face in cold atoms. Yeah, so if you have a Mott insulator, when local interactions dominate, yeah, so that localizes particles down on site, yeah, stabilizes such a state, while if you have, as the other operator that competes, kinetic energy wants to delocalize the states, the eigenstates of kinetic energy are delocalized momentum eigenstates, and that gives rise in a many-body system to the occupation of a single big quantum state, a Bose condensate. So you face, as a function of the competition between kinetic and potential energy, a quantum phase transition between a mod insulating and a superfluid state. Yeah? And that is here kind of depicted a bit more zoomed out. That's the structure you find in any quantum phase transition. Yeah? So you have two extreme limits where it's often even trivial to write down the exact ground state wave function. They do not fit to each other, and then if you are lucky, at a finite competition ratio, you see a quantum phase transition. Okay, we want to ask here basically a very similar question, or if you like, the same question, yeah, in the context of, however, now not just unitary dynamics, but competing unitary and measurement dynamics. We are asking whether there is a similar scenario. And I mean, disclaimer, we are not, by far not the first one to ask these questions. So these two works here were really laying the ground for these investigations. And the setup you've basically already been introduced in the lecture by Saro. Yeah? So at least the unitary part of it, namely what these people study is essentially one-dimensional spin systems, yeah? How they evolve in time. And the state update that is considered here is local, or bilocal, if you like, yeah, gates that entangle two neighboring sites. Yeah? And actually, in the first works, it was just randomly chosen unitary gates, yeah, drawn from some Haar ensemble. And this then is interpierced with entirely local processes, yeah, which really act on a single spin only. For example, the measurement of the sigma z spin projection onto up or down states. Yeah? So that is the competition. Yeah? You have something that spreads entanglement, something that localizes particles down. The extreme limiting cases are very well understood. Yeah? In the case where there's, let's introduce now the analog of this competition ratio. Yeah? And let's choose it, yeah, as the number of measurements that you throw per unit time onto the system over the number of unitaries that you throw onto the system per unit time. Yeah? So this gives a dimensionless ratio, just as a ratio of two energy scales in a Hamiltonian, yeah? Kinetic versus potential energy strength. So now we have such a competition ratio, and let's now look at these extreme cases here. So G equals 0, yeah? So this is the no measurement case. It is well known in these random circuits that this leads to a chaotic non-integrable dynamics, which has it that entanglement growth proportional to the volume of the system, so in one dimension, just proportional to the length. That's really what Saro already told you. And then in the opposite limit, yeah, let's go now to no Hamiltonian dynamics at all, and let's indeed now measure spin up, spin. Okay. Hope I don't have to go again. Good. Sorry. Yeah. How the local entanglement? Oh. I mean, local entanglement. I mean, so you can see it basically from these gates here. So on each pair of sides, you generate entanglement, and if you forget about the measurements, that's what we're doing in this limit here, you can see here I build up some entanglement, yeah, so quantum correlation between these two sides. Then in the next step, yeah, you entangle already this here with this, yeah, so you can see basically how an entanglement front also spreads through the system, and these systems have the property, these random circuits, yeah, so that you really get a lot of entanglement in the sense that it scales proportional to the system size if you wait for long enough. Okay, I can't check, but
we'll probably say
yeah.
Thanks. That's why I'm standing, because showing this way I can kill again.
Very good, thank you.
And I don't have to stand up.
Okay, but that's really, I mean, how the entanglement builds up, how it spreads. Yeah, you can, here you entangle, next step, you go further out, and that's a typical picture. Yes, very good. Right, so let's go to the other limit now. Yeah, so we measure now locally the sigma z. Yeah? And if we do this on every side, and there's no competition from entangling gates, then, I mean, clearly you end up in a product state, yeah, where the sigma i's are either up or down. yeah, because that's the random outcome of measurements, which gives you one of these configurations. There's one thing for sure, there's no entanglement in this state. It's just a plain product state. And I already advertise here so that you keep it on top of your mind, yeah, so that in order to find this and to characterize this entanglement growth, you have to follow a specific procedure. Namely, you have to look at single trajectories, single runs of this measurement dynamics, yeah, which always proceeds in a pure state, as I've explained on the first slide, these two fundamentally distinct types of quantum dynamics. Then one commutes the quantity of interest, for example, the entanglement in the system. We'll define this again. And then you average over the trajectory ensemble. I want to later on explain precisely why these are non-commuting procedures and why this is important to analyze it like that. Okay, good. So in the meantime, just to give you a very brief overview, and then we go into more detail here. Just an overview, so these phase transitions here, I didn't really show what the observation is. Is really missing out. No, right. So there was something missing here on this slide, some piece of discussion. Yeah, what shows in this model, yeah, and that's really important piece of information, what these authors here found is that there indeed is a critical strength for this dimensional competition ratio, below which, yeah, we have exactly the behavior, the qualitative behavior of this limiting case, a volume law in the entanglement growth, in proportional L in 1D, and a saturation of entanglement to an area law in another extended area of this phase diagram here. Yeah? So that is now the important statement. And then I wanted to very briefly discuss what is, so to say, what are the pictures for this transition. So there is, of course, this entanglement picture, yeah, where very roughly, yeah, we get a scrambling of information, yeah, and thereby an extensive entanglement entropy, while the evolution just going from local measurements is disentangling. There is also a picture of quantum error correction, yeah, so that's more this information point of view, so that there's a very fast spreading of information that is actually so fast that it's protected from local errors, and the phase transition is then seen as the transition where kind of an error correcting code would really fail, yeah, and we can extract information really from the state. Yeah? So when we go to the product state, we have perfect knowledge about all details of this wave function. There's also a purification picture, so all these approaches here, they work starting from pure states. You can also start from a mixed initial state, and then there is also a phase transition, which is closely connected to the transition in the pure states, which goes by the statement that an initially mixed state remains mixed if the Hamiltonian, if the unitary dynamics is strong enough, while an initially mixed state purifies if the measurements dominate. And there's also statistical mechanics pictures that have been developed specifically for this random unitary circuits. And then you have to go into the questions that are typical for condensed matter physics. What are the characteristic observables? Are there maybe correlation functions beyond characterizing the problem by entanglement? And yeah, that's very much along the vein that I want to follow here. Namely, the outline for today is this. First of all, I want to just give you a little bit an overview of how measurements can be described. And there is, I mean, the one that we already discussed, these strong projective measurements that are, I mean, really this wave function gets projected onto an eigenstate of the observable. It's called the collapse of the wave function. But there's also a weak continuous notion of measurements, and that is, for our purposes, when we want to work with a field theory, is much more convenient. Yeah? Because then you have a notion of small updates over time, and this will also give me the opportunity to describe a bit the observables that one can use to characterize such transitions. Then I will focus on a very specific model, namely monitored fermions in one dimension, describe the phase transitions just from a phenomenological point of view, and then we'll go into the theoretical description in terms of this problem, in terms of a a field theory which builds on, as I already said, replicating the state over and over again to assess the relevant observables that we developed before. And then if time permits, but no pressure, then I can also explain a bit an idea how to make these transitions visible in future experiments. But let's go first with a little bit of theory background. Let's discuss, I mean, that's something you can learn quite in general, yeah, strong projective versus what is known as weak continuous measurements. Okay, and here is where we start. Again, I mean, I remind you of these projective measurements. And one nice example of a projective measurement is, say, you want to measure the position of a quantum particle on a line here. Then our measurement observable is the X operator, Hermitian operator, which I can spectrally decompose. Now, it's not a sum over discrete eigenvalues, but it's a continuous spectrum of this operator. And here I introduce this notation that I already used previously with this P lambda operator here. So that's a projector onto position X, onto one of the eigenstates of this operator X here. Okay, good. Then the measurement outcomes of this process here are, of course, what is here written. Lambda is a continuous variable x naught can come out. And as I said, the projector onto that state, when the measurement outcomes was exactly x naught, is this one here. And let me now, for the fun of it and for the next slide, rewrite this as an integral over the whole set of eigenvalues with a delta constraint. That's a trivial way of rewriting this. And the important feature is that after such a measurement process, we really know x naught precisely. So it's totally known where the particle is after this state update. So that's copy-pasted. And then we realize that if we do anything real in physics, things take time. So there is no really totally instantaneous collapse of the wave function. Of course, you can postulate that. But another way of thinking about it is there an issue?
No, I'm trying to get rid of that.
Okay, yeah. That's very nice, because there is a little bit of information down on the page. What I want to say is let's soften this delta function a little bit. Let's just move it, let's just regularize, if you like, this sharp delta function by a Gaussian, which has the property that, I mean, if I really go formally to this instantaneous measurement limit, and I send delta t to 0, so then this Gaussian function sharpens up and converges to the delta function. So then we get back the projective measurements in this limit. On the other hand, I can write then this operator using the spectral decomposition here. I can write this back into a Gaussian operator. So a Gaussian operator, e to some quadratic form. That's something that we are also familiar with from unitary evolution, e to some harmonic oscillator, that's x squared plus p squared with an I in front. Well, there's no I in front, but that's also not unitary evolution that we are describing here. Okay, and while the strong projective measurements are obtained in the limit where delta t goes to 0, and the weak continuous measurement are those where delta t becomes actually small, but at the same time, we measure it very often. So, in fact, this is exactly the limit that we're used to, or that we got to know when constructing a path integral. We send the measurement, the observation time to 0. We send the number of measurements to infinity, but we keep the product of t times n, so that's the chopping of the trajectorization. We keep that constant. That's really analogous to the functional integral construction. And that will be the idea, or that will what we can technically use when we want to map measurement problems into path integrals. So then this continuous measurement formulation is much more convenient, and I'll discuss also at some point how these actually relate, if we should expect phase transitions as a function of sending delta t from 0 to infinity. That comes later. Okay. But what is lost now is the ability to move. I have to once press it here. Yes. Okay. Good. So now let's remember what we did yesterday, no, the first day, I think. We had in quantum problems, yeah, we had always a probabilistic formulation and a stochastic formulation of a problem. Yeah? Now I want to argue that this here is a kind of probabilistic formulation, and I want to transform it into a stochastic one where there's an explicit element of noise going on in the problem. Okay, and to this end, yeah, first of all, let's introduce this probabilistic measure here. Yeah? So here is the Born probability, yeah, for measuring the expectation value of this operator A, which I can write here as the trace of, I mean, that's just a definition, yeah? So that's how this is defined, the trace of this A dagger A object here. And A, yeah, as we defined it on the previous slide, yeah, so that's this slightly softened delta constraint. Okay, now I want to convince you, yeah, so that this measurement outcome x naught, in the case of these weak measurements, can be really seen as a Gaussian random variable. Yeah? So the Gaussianity, in some sense, I mean, you could say it's now obvious. Yeah? So there's e to the some quadratic form. It's a Gaussian variable. But let's make this a bit more precise. So what we need in order to characterize a Gaussian variable? What's typical there? Mean and variance. Right. So just look at that. Yeah? So let's just look at that and a bit more slowly. Please ask questions. Don't forget. Right. Maybe I go a bit slowly to look at this P of x naught. Yeah? It is defined as the trace of A dagger. There is a question?
Yeah.
Great.
One question.
Yeah.
Here you are softening the projective measurements here.
Mm-hmm.
The
Mm-hmm.
representation of the delta.
Mm-hmm.
But since there are multiple representations of delta function, do you expect the same? Do you choose this one simply because it's easier for doing calculations?
Mm-hmm. Mm-hmm.
Or do you expect that a different representation leads to different results?
Mm-hmm. Very good question. I mean, you have to eventually, yeah, I mean, this is a model for a specific measurement procedure. And what is in back of this precise procedure is that you have essentially, I mean, that would lead now a bit far out, yeah, but what is behind this precise regularization, yeah, is that you have a system that you immerse into a bigger environment, yeah, and this environment, you prepare it in a Gaussian state, yeah, and then you measure actually the environment projectively in this, and you couple the system that you want to measure and the environment only weakly. Yeah? So you get only a weak entanglement, and therefore you acquire only little information when projectively measuring the environment, and this Gaussian regularization of the delta function comes out if, and that's really construction of your whole measurement apparatus, if you initialize this in a Gaussian wave function. So it's a physically motivated regularization that I indeed, I mean, you can do that, you don't have to do that, but this is very benign. It's as you can choose different Hamiltonians. The question is, an interesting question is then, how strongly, for example, do phase transitions depend on such a choice? Yeah? I have some remark on that later on, but you can ask then again if you like. Very good. So we want to represent this thing here, right? And instead of writing this here, I directly unravel this trace into what it really is. Namely, it is psi, yeah, for this pure state. These operators here, psi. And now I can just insert here a resolution of identity. So and then inserting the definition of what this A dagger A is. Yeah? So this guy gives me a real space representation of psi here, and this guy finds this psi, gives me a real space representation of psi star of x, and I just copy these operators here to find with a proper prefactor 2 gamma delta t 1/4 squared, so to the 1/2 over p, and then integral from here dx e and the square x naught squared psi of x absolute value, where in addition I have used so that the e to the x hat operator acting here on the eigenfunction on the position eigenfunctions spits out a number, the number that's popping up here. Okay, and from that we can then easily get, that's an interesting relation, the expectation value of x naught, this random variable, with respect to this probability distribution, which is just defined, let's just define that as usual. If you have a probability distribution, P of x naught, then this here is the expectation value of x naught. And here is then the prefactor, and we integrate dx naught. I copy dx x naught e to the 2 gamma x minus x naught square psi absolute on x, and then nicely I can do the x naught integration, just shifting the Gaussian. And the nice prefactor here was chosen to just under Gaussian integration produce me unity. So here I get really, to see what stands, dx, right, so under this x naught integration was also an x naught. So what's the Gauss integral or what's the expectation of x naught with respect to this variable x here? Well, it's just x, right? And then I copy paste psi x absolute square. So this came from the Gaussian integration over x naught. And the interesting thing is now that we recognize here the quantum mechanical expectation value of the position operator x. So the measurement expectation value of this variable x naught coincides with the quantum mechanical expectation value of this position operator. So that's an interesting observation. Now where is this bloody little, here we go. And well, now you can go on and compute the variance. If you now have followed this calculation, I think it's easy to read off. It's the same argument. The variance is essentially 1 over twice this guy here. So it's this object here. And with these properties in mind, so we have now an expression for the expectation value of x naught, for the variance of x naught. And with this, we can indeed transit from this probabilistic formulation, where we speak about variances and so on, to a stochastic formulation, where we treat now really this x naught as a Gaussian random variable, which is characterized by its mean, which we identified as a quantum mechanical expectation value, plus a fluctuation here, which is parameterized precisely in this way that if I now look at the variance of this x naught as a stochastic variable, it reproduces precisely this here. So this is this transit from a probabilistic formulation, where we speak about variances and probability distributions, to an explicitly stochastic formulation of the measurement process. And it's really similar to what we discussed at some point, so that we have this structure of probabilistic formulations into which we counted, for example, the Lindblad equation, the Fokker-Planck equation as a classical limit of the Lindblad equation, the stochastic formulations that was rather than Heisenberg-Langevin equations or Langevin equations in the semi-classical limit. So now we are about to reformulate the measurement as a stochastic process. Okay, right, and the stochastic update of the wave function, as we do it with projective measurements, we hit with the operator a hat of x naught onto the wave function, and we rescale the wave function then with the according Born probability. Okay. Then for short observation times, we expand here to linear order in this delta t, and that is something that is now half a page of but pretty straightforward calculation. Really what you do, you just expand this here, so dt, you look at the small update, small dt, and you also account for the expectation value in the denominator. That's what makes an appearance of these expectation values here and there. And you take into account this, this explicit noise increment in this limit. There is a subtlety that I sweep under the carpet if you want to. So how one has to count actually the powers of delta W, but that's, I mean, something that I think is a bit beyond this shorter lecture here. Okay, any questions on this? So that's an important conceptual step. No? Okay. Good. So what we then end up with is this object here. It's called a stochastic Schrödinger equation, and it involves this what is also called as quantum trajectories here. So we look at the state update at the increment of the state here on a small time window dt. And so what I've described in some detail is this piece here. So now instead of measuring a single operator m hat, I'm already transiting a bit into this many-body problem that we want to analyze here. And I look at a many-body variant, just as in a Lindblad equation. You can look at one single degree of freedom, or you can just look at an array of them. So I'm here psi L, imagine this as labeling the sides of a lattice, and I'm measuring here, I'm monitoring the local particle number on this lattice, side L. And then again, we have this characteristic structure. This is a term that looks like decay. Then I also added in a Hamiltonian here. So that's the usual state update that goes with one step is IH. And then there is this stochastic, explicitly stochastic element up there. Okay, and again, so the expectation value of this operator is defined in this way. So this works not only for continuous variables like the x that we looked before, but also, for example, for this discrete variable or variable with discrete eigenvalues n L that we're looking here. Or say also spins, you can look at spins with projection plus minus 1. Okay, there is now one interesting feature that I would like to point out, and that is how do we recover the idea of the collapse of the wave function in this formulation. And to this end, it's useful to set the Hamiltonian operator already directly to 0. And then we have this structure here. We can think about when, so set Hamiltonian to 0. No competition at this point. So when can we expect that this evolution comes to an end? So when does this evolution acquire a dynamical fixed point, if you like? And that is the case. So this noise here will wiggle the system around all the time. So this we cannot switch it off. That's intrinsic to the probabilistic or stochastic nature of the measurement process. But what we can do, and that's different from this Langevin equation that we've seen. These Langevin equations, they always had the structure something like d phi equals some reversible Hamiltonian d phi plus some imaginary, some dissipative terms, and then some noise psi. So this is running all the time. You can't get rid of it. Even if you switch off these terms here, this variable will be kicked around by this noise. Yeah? Now here we have a structure that allows actually for a dynamical fixed point, yeah, or for the evolution to come to rest, namely precisely in the situation that this equation here is solved. Yeah? Because if this is true, yeah, so then this part here will just go away. Yeah? So this will vanish. So then we have to ask, so under which circumstance do we solve this equation here? Yeah? And you find a self-consistent solution to this equation if, indeed, the system is locally in an eigenstate of the local density operator. Yeah? Because in that case, NL hat applied to psi equals, so this is the eigenvalue condition NL, and just unit normalization. Yeah? And therefore, you can see that in this case, yeah, so this becomes NL, and we self-consistently solve this eigenvalue equation. So therefore, or one way of formulating that is kind of that there is a dark state, or that's just the name now that we choose for that, a dark state of the measurement operator, yeah, or of this part of the dynamics here, is taken when the system has really approached an eigenstate of the measurement operator. Yeah? And the picture that you can have in mind here is that the wave function doesn't collapse indeed instantaneously into the eigenstate of the measurement operator, but this is at least what happens in the course of time. Yeah? Exponentially quickly, yeah, the system reaches the an eigenstate of the measurement operator, and yeah, that is what one can refer to as a continuous collapse of the wave function. So here, let's initialize the system here, yeah, where there's, I mean, totally flat probability distribution. And then, I mean, if we measure here spin 1/2, the possible eigenvalues of spin 1/2 is plus or minus 1. And then you will see, yeah, so that over the course of time, if there's no perturbation coming from a Hamiltonian, then really the system finds one of these, or builds up a probability distribution which is exactly peaked around the two possible eigenstates of the measurement operator. Okay. Good. So then we can ask whether we should expect actually a measurement-induced phase transition similar to the case that I discussed for the strong projective measurements. So, well, I mean, it's already there, but I mean, any comments on that? It's maybe a bit boring, yeah, so because it stands here. I mean, the point is, yeah, so when do we get phase transitions? Yeah? So we get it when operators do not commute. Yeah? But if I choose now measurement operators which are in the, whether I send this delta t to infinity to collapse to projective measurements, or let delta t small, yeah, these two sets of operators, yeah, for a choice of delta t large and a choice of delta t small, they of course still commute with each other. Yeah? So they are just, both of them are built of the x operator, yeah, of this measurement of the x operator, weak or strong. And therefore, I mean, these two measurement protocols, yeah, and that's now with respect to your question also, yeah, these protocols, they do not lead to any competition. And therefore, while one may expect, yeah, so that the phase transition maybe bends a little bit around, yeah, because the non-universal properties, yeah, the details of the measurement process are different, and so the very existence of the phase transition and possibly also its universal behavior should not be affected by that. And the big advantage, of course, as I already advertised, yeah, of these kind of measurements is that we can formulate a field theory based on the continuity in time that we have here. Questions about this part? I don't know. I mean, the last days you were much more active. I don't know if I'm going too fast or if it's the end of the week. Or I encourage you again to participate a bit. Yeah. Okay, good. So now comes this point, yeah? How do we analyze, how do we get information from this setup? Yeah? And that's kind of really ironic. Yeah? We are measuring the system, and I will tell you now that it's very hard to get information out of that. Yeah? So although we are measuring all the time, you would think naively, well. But okay, so what is the problem? Yeah? The problem is that psi of t, yeah, as we just really elaborated, yeah, so we formulate the problem in terms of an explicit noise element that's around, is really a random variable. Yeah? So from a random variable, you never get information from a single shot. Yeah? You have to find a way to build statistics from that. Yeah? And I will now tell you what does not work, and then how it can work. Yeah? So the problem can be formulated or can be identified, can be narrowed down in the following way. Let's look here at the stochastic Schrödinger equation that we just wrote, but let's rewrite it a little bit, yeah, in terms of this projector, which has the structure of a density matrix, yeah, of a pure state. On each run of the trajectory, we're looking at pure state dynamics, right? But it's just, I can write it in this outer product way, no problem. Yeah? And then we get this structure here. Yeah? So there we recognize the Heisenberg commutator. That's these conjugate states that come in. Here is then a piece that looks really exactly like a Lindblad equation, yeah, for a specific choice of Lindblad operators, namely our measurement operators NL. And then there is also this, in addition, this piece down there, which involves this explicit occurrence of the stochastic element. Now, the problem is this. Yeah? If we look at usual observables, yeah, if you look in the book on quantum mechanics, yeah, all observables are linear in the state. Yeah? And what is meant here, I can write them, yeah, linear in the projector on the state. Yeah? So that is how you define the quantum average. Yeah? So that's just, I mean, that's for a pure state, and I can rewrite this as a trace with a state projector. Now, if we average over all trajectories, all these stochastic processes, yeah, as in the Langevin problem for the classical problem we looked at. Yeah. So then, I mean, we have to work with this averaged projector, or I mean, this average. Let me put it like that. It really doesn't act on the observable. That's just an operator independent of the state. That's just this linearity in the state. It only affects this average, the state here. Yeah? And the big problem that we can immediately see, yeah, is that this state average here is proportional to the identity. Who sees that immediately? You see it? Very good. Yeah, but let's, because not everyone showed up, let's justify this. Yeah? So why is the statistical average of this density matrix really unit matrix? Yeah? So we can read it off this equation, and we just average to get the evolution of the average density matrix, really the density matrix of this problem. We just average the entire equation here over all possible realizations of the noise. This noise here was defined to have 0 variance. Yeah? And then we get an evolution equation for this rho bar, yeah? Rho bar of t, yeah? Because we average over all possible configurations. So then this term goes away, and what we really end up is here a Lindblad equation, indeed. And just to bring this argument again, whenever we have Hermitian Lindblad operators like this, where's the 2 here? Like this, yeah, you can see that the row chosen proportional unit matrix here solves this part. It doesn't gives a dynamical fixed point. It annihilates this part here of the generator of dynamics simply because I can write it like that, and all these terms here, they cancel each other. And the same is, of course, also true for the Hamiltonian. It commutes with the unit matrix clearly. So, and the news is, or the statement is, that it's not only one solution, it's also a dynamically stable solution very oftentimes. So you can have many other solutions. Yeah. Was that the question? For example, if you have any mod state or so, is also a beautiful solution of this equation. But in the moment, and it would actually be a stable solution for the measurement dynamics of this type alone. But in the moment that you have a Hamiltonian, so that kicks you out of these specific eigenstates, so then the only solution that, I mean, it's more an observation than a mathematically precise statement, so that another way of saying this, so when you put these type of operators, these n measurements, so this is physically dephasing, so you are always, and this dephasing comes because you couple physical particles, say in an optical lattice, to the driving laser. And then what this laser will do, it will just heat up the system to infinity. And that's an intuition behind this infinite temperature state. Yes, it's a second law of thermodynamics, if you like. The entropy of a state will always increase unless you do something very special and not decrease. So, and for example, if you couple to a laser, that's the physics. I mean, we can construct a special example. For example, if we switch the Hamiltonian to 0. So then you have these, what I said, mod states. Pure states, which are dynamical fixed points of this. And then, of course, but my intuition is that whenever you go out of the eigenstates of the n operators, so then you're lost. So, and any standard Hamiltonian, so any Hamiltonian which is not exactly local, which is a little boring physically, that will kick you out of that.
The specific unraveling, I mean, the specific stochastic showing the equation to be obtained potentially also from an unraveling of the what to study, unraveling the frequencies. And in this case, as far as I understood, it's motivated physically by coupling the path,
right.
Yeah. So here, this stochastic showing the equation has a physical meaning.
Yeah.
But I was wondering if I didn't design a specific protocol and so I had in blood that I do another
Yeah.
because I don't know, I want to study dynamics and for instance I want to observe if I observe a transition. Would observe with any unraveling or there is a dependence?
Yeah, I think that hits precisely the question that we discussed. Yeah, so this, I mean, in the sense, so that what I would expect, so is maybe that the non-universal properties of the phase transition, they might be changed by your precise protocol, but everything that is universal, so say, I mean, like the basic structure of the two phases in this problem. So the critical behavior of the phase transition, these things I don't expect to be changed by that. So it's really, I mean, a kind of short distance modification. So non-universal details, but problems like phase transitions are typically very insensitive to microscopic details. So as long as we don't introduce, I mean, non-commuting operators. But I mean, the exact example you were specifying is, I mean, it's just a different unraveling. The same argument that I already told. It's essentially commuting operators. So, and you can smoothly connect these protocols.
For instance, so the critical point will change.
Yeah. So exactly.
Because I'm wondering about how to observe things and so on.
Yeah, I mean, I think maybe the best way to think about it, I mean, you can smoothly connect these protocols without ever introducing operators that do not commute with each other. So it's just different extreme limits, but they all stay somehow without qualitative modifications without introducing additional non-commuting operators, because we are eventually measuring the same observable. I think that's the best thing I can say. Yeah. Yeah, I mean, this is, so to say, what happens in a long time limit. Right. So, I mean, very good. Yeah. So, I mean, we will always be interested in the setup. Yeah. So, let's say we have a 1D system here, and then we want to evolve it over time. Yeah. And all questions I will ask are, so this is after some initial further, just, I mean, really to get into the problem here. Good. But I see you waking up. After. Very good. Okay. I wanted, oh, yeah, right. I wanted to give you maybe a little bit more intuition. Yeah. So another way of looking at this problem, yeah, is the following. So you may ask yourself, but then how can there be so structurally different entanglement properties if I always produce this unit matrix stationary state? Yeah? So that sounds, I mean, also to me was super counterintuitive. There should be some difference, yeah, if in the average state, yeah, if the states are either strongly entangled or not. Yeah? But to this end, I would like to give you this intuition here. Imagine a device, and that device produces, on the one hand, a set of wave functions, yeah? Just 2 spins. We take 2 spins. And in one device number A, it produces product states for us of these 2 spins. And each with probability 1/4, the rule of the game. The other device produces wave functions psi b, which are, however, so these are unentangled. Now the other device produces states which are entangled, and let's say for spins, for 2 spins, these are exactly the 4 Bell states. And again, we have as a rule of the game that they be produced with 1/4 probability. Yeah? And now the interesting observation, while these states are very different, each of them, yeah, and if I quantify entanglement for these guys, it's 0, and if I quantify entanglement for these, it's log 2, yeah, it's cutting the single qubit. The density matrix that I produce from the ensemble with equal probabilities rho A, I get 1/4 sum A psi A. And this is a beautiful representation of unity, up to 1/4. So this is a normalized state. And if you now, maybe you do it for yourself, if you take these entangled states and you build the ensemble with 1/4, it's exactly the same as rho B. Yeah? So this is, you can represent the unit matrix, yeah, this infinite temperature state, either in the basis of product states of your Hilbert space or in the basis of highly entangled states, but the average density matrix really does not know anything about whether it is constructed from entangled or from from product states. And that is really why, I mean, that's a totally different look at this statement here, but it's really the same thing. The average density matrix does not care about whether it's built from entangled or product states. And so it's a different point of view, but the same statement in the end. Yeah? So if you like, yeah, so we have here an assumption, yeah, so that all the trajectories come with equal probability. That's the same statement as, I mean, this device produces these states here with equal probability 1/4. Okay. I think that's really a crucial point that, I mean, that one to digest the problem. Okay. Good. Oh, what's happened there? Right. So the solution, how do we circumvent this problem? This is like this. Yeah? we can, at least on a piece of paper or on a computer, we can look at observables which are state dependent. Yeah? So now we are going a little bit out of the paradigm of standard quantum mechanics, yeah, by looking at operators O which themselves depend on the state. Yeah? Why is this promising? I have no more to say than this relation here. At least it's not clear it doesn't work. Yeah? Because for a nonlinear function, yeah, of rho, of some variable rho, yeah, the function of the average is not the same as the average of the function. Not more, not less. Yeah? So at least there is now a chance, yeah, of gaining something. And examples for such nonlinear in the state functions are, of course, the entanglement entropy. Yeah? So as Saro explained, yeah, so this entanglement entropy is defined as, well, let's first trace out half of the system here and compute the reduced density matrix rho A, and then let's compute the expectation value, yeah, for this O. We take log of rho A. Yeah, so it's a highly state-dependent function, yeah, called entanglement entropy, but it's at least the concept is it's a highly nonlinear in the state function, and it has a chance, therefore, evading, yeah, this bad averaging effect when you build standard quantum mechanical observables in this way. Okay, and another example, let's maybe not be so greedy, yeah, is this correlation function here, which is, which would be quadratic in the state. Yeah? So something that, yeah, here is an occurrence of rho, here is another occurrence of rho, so conceptually this quadratic in the state, and only after building this, I do the average. Okay, I'm going extremely slowly, but still, last piece of intuition, then we go into the concrete model here. So let's look at a toy model to again illustrate this. Yeah? We have here, let's look at a model where we have just a single fermion particle, yeah, a fermion, on two sides, and we monitor locally its density, and we let it hop from left to right. Okay, and then one thing I already said, if the Hamiltonian is totally zero, yeah, then over time we will collapse in either of the eigenstates. Yeah, the single particle can localize either here or there. Now we go to a strongly monitored regime, yeah, where we switch on only a little bit of Hamiltonian, yeah, a little bit of this hopping strength J. Yeah? And then what you see when you just evolve the wave function of the problem, you see it gets pinned to the eigenstates of the measurement operator, so it's either at 0 or at 1, yeah, and only in kind of instanton-like transitions, yeah, it is on its way, so to say. Yeah? Conversely, if we are at weak monitoring, then we get these basically Rabi oscillations, and the system transits between the eigenstates of the measurement operators, and in particular, you're basically never there. You're basically never in time in these eigenstates of the measurement operators, but you are going on Rabi oscillations. Now, if you solve this problem and you look at the linear averages, you see nothing of these qualitative differences in line with what we said. We're evaluating with respect to the infinite temperature ensemble. So these correlation functions here are totally signal-less, totally flat. Conversely, if you look at such a nice guy here, yeah, that is nonlinear in the state by this object here, you see at least some qualitative dependence. Yeah? And you're asking always about the nature of phase transitions. Yeah? So that is now what guides us, really. Yeah? So we have no better argument at this point of the possible expectation that if we go, yeah, from two to many sides, things may become sharp. Yeah? So something that is here really smooth may develop, if let's see, yeah, into something that is sharp in the thermodynamic limit. Yeah? And the second thing, and indeed we will get out with a picture, yeah, which goes like there is a phase in which the particles get pinned to the eigenstates of the measurement operator, and then a phase where they depin and they go over the whole system. And that will be the intuition for the phase transition that I want to explain now. Okay, and this will be signaled, yeah, in observables, quote unquote, that are like this covariance matrix or something like this. Yeah, if we go from to many sides, and not N1, N2, and I and J. Okay, so and the precise model that we want to look at is a Hamiltonian, which is just a kinetic energy, so it let particle hop. And the monitoring, we go for this local monitoring of the particle number. Right, here is the model again. So this is the dynamics we want to study, and the competition is between this Hamiltonian here, which by itself, as Saro also explained, although it's an integrable model, if we initialize it in a random state, it will give us a volume law entanglement, while these measurement operators, they lead to the collapse, to the soft collapse of the wave function, as we explained. And therefore, if this is the only resource of dynamics, we get an area law entanglement entropy, because we're collapsing into this product state in the end. And we have to respect this caveat. We have to build the proper observables, as I said. Now here is the phase diagram, first the phenomenology, and then why this happens. This is what one finds numerically here. So on this axis, we have the competition between the measurement and the hopping. So here we are in the weakly measured regime, and what one finds for very large system sizes, down here is the thermodynamic limit on this axis, one finds that a log growth of the entanglement different from this precise point here, where if we not measuring at all a volume law type phase where the entanglement entropy scales proportional system size is really unstable towards the smallest amount of measurement. And that is really an extended phase with this log scaling, while if we measure very strongly, then I mean we get an area law, because at some point these measurements win. Okay, so here is some details for that, but the real point is that we get an extended phase, or like a critical phase, where the entanglement entropy scales, and it scales logarithmically with system size. Okay, so here are some observables that witness this, and an important point is it's not only really in the entanglement, but anything, as I kind of tried to argue, anything that is nonlinear in the state has the potential to signal these transitions, and indeed you can here see essentially all the qualitative features of the phases in the qualitative scaling behavior of this correlation function, of this density correlation function that we're looking at here. I spare you the details on this, but when we now go for what is the nature, what can we say about the nature of this phase transition, then we have this observation here. So we look at the entanglement scaling, and basically up to details, so that are for L to infinity, they are not so important. You see here a logarithmic scaling with the system size, and here we are looking at the coefficient. What is the coefficient of this log here doing when we crank up the measurement rate? And you see that in a rather small window of gammas, of measurement strengths, it really drops by orders of magnitude. And that smells a little bit like a phenomenon that I briefly mentioned, at least. It smells a little bit like the phenomenology of a Berezinski-Kosterlitz-Thouless transition, so this phase transition that occurs in two-dimensional systems with a continuous phase rotation symmetry. So this phase transition, this Berezinski-Kosterlitz-Thouless transition, also has a kind of jump feature at its transition, which, however, doesn't appear, of course, in the coefficient of some entanglement entropy, but rather in the superfluid stiffness, in how the system responds to rotation, externally imprinted rotation. It's just a phenomenological observation at this point, but indeed, if you go a little bit more quantitatively and you pretend that this quantity C, this coefficient, has the scaling behavior that you expect for a Kosterlitz-Thouless transition, then you can verify that. At this point, no deeper justification, but we'll come to this next. Right, so let's therefore now study how we can approach this problem in a field theory language. Let's first set up this problem. Yeah? So how can we formulate even this problem? And so we start this problem from the weakly measured regime. Yeah? So again here, no measurements, yeah? And now we are looking in the vicinity of that. And what we are going to try, yeah, is to whether we can go a little bit along this way until we see or not, yeah, a phase transition. So it's an expansion about the weakly measured regime. And what can we say about this weakly measured regime? Well, we just look at the pictures here. Yeah? What is shown here is as a function of x. Yeah? So this is x. This is the color code for the density that we're showing. And here of time, yeah? We track the expectation value of the local particle density. Yeah? And what you can clearly see here, not only in the initial time regime, but also later on, yeah, so there is a kind of ballistic spreading of these particles, which one can capture, yeah, by taking these fermions that are sitting on the lattice to begin with, but going to a continuum limit, yeah, where we introduce left and right moving particles. Yeah? And the velocity is basically given by this by the speed with which they go out. Okay, so when we want to formalize this, yeah, and to go to a continuum limit, yeah, so also in space, so we have already discussed the continuum limit in time. That's our weak continuous measurements. Now we introduce a continuum limit also in space. Yeah? And that is, so to say, really guided by these left and right moving particles. And that is a standard construction that this gives rise to then a so Dirac Hamiltonian, yeah, which has here this characteristic matrix sigma z. So the entry 1 in the sigma z matrix that describes the right moving particles, and -1 the left moving, just in the other direction particles. Yeah? So that rationalizes this matrix sigma z here. Okay, and there's one black box that, yeah. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Very good question. So the picture, as a first of all, you see that something like, I mean, if you ask, can we do that, then I refer you to these pictures, yeah, which clearly show that there is a ballistic spread of the particles, although we are measuring the particles. Yeah? And my picture is, I mean, so these measurement operators, yeah, so they project, so we have say the fermions, they start with this kind of Briand zone here. So this is momentum of the fermions K. So this is the lattice structure that these particles have. Yeah? And the kinetic energy favors eigenstates of that. Yeah? So a totally local measurement of particle density spreads you out over all momentum modes, yeah, because of the Fourier conjugate. So we will occupy here randomly, yeah, by the local measurement all momentum modes. Yeah? And you can see kind of that from all of them sort out these, after this measurement process is still sort out these ballistic fermions. Yeah? And you can now go into more detail, yeah, and you can find, yeah, when you really go a little bit deeper, you find really that these points here that are distinct by a specific phase relation, yeah, so that these really the points with the fastest velocity are those that really are the proper low energy or the proper degrees of freedom for this problem. You can see that from just looking at what's the typical V that sorts out, and you can convince yourself that it's a V around these points, and you also have analytical arguments for that. Yeah. More questions? But it's important, yeah, because that is, so to say, our basic assumption, yeah, that we can take this lattice or these lattice fermions and then move to a continuum description of this problem. Yeah? So that, but let's be very clear, it's still an assumption motivated by this observation. if this is admissible, then we can bosonize this problem. So we can switch from a variant of this model representing fermions to a bosonic formulation of the problem, where we have here the variables are a phase variable and a density variable. So that's really the Lattinger liquid construction. So that tells us we can switch from this Dirac fermions in 1D to bosonic variant of the problem. And that's much more benign to analyze. Same way, we now formulate the measurement operators. And this big psi here is just collecting the left and right movers here. And there is, when you expand out, so this, well, I shouldn't do it, so the density operator into this left and right moving modes, you find two contribution. One looks like that, and in the bosonic variant, it's a bit like a black box, but watch the structures that are coming out. One of these combinations here becomes a linear and gapless bosonic operator. So gapless means it carries a derivative in front. And the other one, so the sigma x sandwich, connecting left and right movers actually, that gives a nonlinear term in the bosonic formulation of this problem. Now, if we just look at these operators, so this phi here signals fluctuations of the density. So we see that the measurement operators also in the bosonic bosonic language, so they have eigenstates of the density. So because, and they stabilize exactly this product of density eigenstates. But there's also the competition that we had in the original model that is here represented in terms of these phase fluctuations. So also in this bosonic variant, even if we didn't go through the detailed steps, you preserve the competition of the underlying model in the sense of we also find here non-commuting operators. The phase, the theta and phi, the density, they are conjugate variables in quantum mechanics, and this leads to the competition. Okay, now the next thing in our construction will be to think about how do we get access to these correlators here. So that's, you have to work a bit. And that is where this replica construction comes in, that we later use in the Keldysh integral also. So what we do, we just copy this wave function. Here we introduce copies of the wave function in this way, so really exactly the same configuration of fermions shows up in these two copies. And the statement is, that I will demonstrate now, the statement is that we can get this correlation function, which is nonlinear in the state, as a linear statistical average of this replicated density matrix. And then that's the trick. So then we can compute now from a linear statistical average of a replicated density matrix these nonlinear in the state averages. And let me demonstrate this just in a second. So, right. The claim is that well, our row twice replicated is this here, psi1, first replica tensored with the second one. And then we introduce now density operators, which act on replica number 1, and another one which only acts on 2. Okay, and then the statement that I want to demonstrate is now that the following thing, 1/2 the trace of n1 minus n2 y with respect to this row 2r, which maybe I write again. that this thing here, that this is precisely the C, the correlation function between positions x and y, which is the one that we would be interested in computing. So this thing nonlinear in the state. And that's really, you just have to use the definitions. So this nx1 and nx and y1, so that will exclusively act on this wave function here, while in this combination we have nothing acting on psi 2, and therefore this gives just a normalization. So this gives me 1/2 nx and y average times 1. Now if you look at this, these two guys, this exclusively acts on the second part, but it's really the copy of the first, so we get the same value eventually. So, and the first one sees nothing, sees the unit operators, so we get 1 times nx and y. We are all the time using really that these are exact copies, nothing in no digit different, minus, and then we have to track, say, this guy here with n1 with n2, and so those, one sits on this and the other on this, so this gives us nx and y, and another, the remaining combination, another ny and x. So, and then with this factor of 1/2 in front, we exactly build up this, this correlation function. So in the upshot, by introducing these replicas, we can compute these nonlinear in the state here quantities. Okay, and now we do nothing more and nothing less than computing essentially the time evolution of this replicated density matrix. And later on, we'll also look at the time evolution of a replicated Keldysh functional integral. But it's pretty instructive to look at this problem here. So here you can see that actually it basically looks very much like this heating Lindbladian. We get really so sorry, this double commutator structure is something that is maybe not so easy to recognize, but in the moment that we have here Hermitian Lindblad operators, you can rewrite this here as a double commutator. In this way. So this is just a rewriting. But you should recognize with this here, or I tell you, you can recognize really precisely the structure of this heating process that we had before. But there's now some interesting difference, namely the coupling between these replicas introduces this fun term here, which has really no counterpart in the average Lindblad evolution. So now let's try to make sense of this guy. We want to study the structure of this two-replica theory. And to make our life a little simpler, let us first look at the case where our measurement operators, we approximate them by the simple piece, by the one that is linear in phi. And here was another piece, this was this cosine nonlinearity. Let's discard this for the moment to see a bit better the structure. And then, I mean, the interesting insight was that we can change coordinates very much like this Keldysh rotation that we discussed, but now we do a kind of rotation in the space of these replicas. We introduce center of mass, average coordinates, and relative coordinates. So this relative coordinate, very much like this quantum field in the Keldysh, which measures this difference in field configurations on the plus and minus contour, this coordinate now measures differences in configurations between different replicas. Okay, so, and what we find then, that in the case that we discard this nonlinearity, the master equation in these coordinates for this replicated becomes separable. Meaning, I can make an ansatz for the total row as a product of a density matrix exclusively for the average coordinate, and that looks like that then. And this describes, if you solve this equation, this describes heating up. It only has this quantum jump term, while this relative replica coordinate shows a cooling, yeah? So the one heats up and the other one only cools down, yeah? So, and that is really by this, so there's only dissipation here and for the relative coordinate, and there's only fluctuation for the absolute coordinate. And it's just, I mean, it's not that it's, this is what this problem wants to tell us, I guess. Yeah? So this absolute mode heats up, the relative mode cools down. There's no jump term in this, no fluctuation, only dissipation. Remember this splitting of the Lindbladian into dissipation and fluctuation? That's here what happens, but in factorizing these degrees of freedom. And of course, therefore, yeah, because we are cooling into a single state by this dynamics, we can further separate this evolution here into, I mean, a non-Hermitian Schrödinger equation. Yeah? And that is the Hamiltonian that governs this non-Hermitian Schrödinger equation in the case, yeah, that we neglect these nonlinear term that we also produced. Yeah? So let's now think what happens if we take into account this nonlinear term. Yeah? And I said we work kind of perturbatively in the measurement strength. We want to expand our problem about the weakly measured limit. Yeah? So that's our setting. So we should be able to work in some sense perturbatively in this. Yeah? And let's not go into all details, but I just tell you that the outcome of this construction, yeah, when there is then a weak coupling between this average mode, which heats up, and this relative mode, which cools down, but in such a way that we can totally integrate out the average mode, and the result is then an effective non-Hermitian Hamiltonian. That's the one I discussed previously. But then there's also this nonlinearity popping up in this problem. Okay. And this problem here looks really exactly, or this is a Sine-Gordon model. Yeah, so it's called Sine-Gordon. So there's this cosine nonlinearity. That's why it's called Sine-Gordon model. It's called Sine-Gordon model because if you look at the equation of motion, and you take one derivative of the cosine, it becomes a sine. So that's a Sine-Gordon model. And what is kind of well appreciated in such models is that, I mean, what such a cosine nonlinearity can do, it can drive you out of this gapless phase here and lead to a pinning of this variable, that's the argument of this cosine, into the minima of this cosine function. Yeah? And that would be exactly so that the particles really localize down to eigenstates of the particle number measurement. Okay. And to make this here more manifest, this physics, we move to a path integral. And the action that governs this path integral, so this is really just this idea because we had this separation. So we evolve here a psi, now under a non-Hermitian Hamiltonian, and we do really exactly this. Yeah, on a single contour, we construct the path integral. That is the action corresponding to this path integral. That's in the exponent of this path integral. And if one then tracks the renormalization group flow of these coupling constants, yeah, which are complex numbers in general, in the standard Sine-Gordon model, these are real numbers. Yeah? And then we can ask, well, now, with these complex couplings, how does the renormalization group flow go? And the interesting observation is that we always converge to the flow of the real couplings. Yeah, so in one sentence, yeah, so this problem at long wavelengths, when we go and do RG transformation on these couplings, yeah, they just collapse back onto the totally standard Kosterlitz-Thouless flow equations. Yeah. They become real. Yeah. So they really, I mean, here is the red ones are the Hermitian, as is the real couplings, and the black ones are the full ones. And you can see they really want to approach this point. Yeah. And what this then tells you, and then it's a with this observation, yeah, it's then a self-fulfilling prophecy that we have a phase transition, a Kosterlitz-Thouless phase transition, yeah, which goes like that. Now, as a function of measurement strength versus hopping, Yeah? In the Kosterlitz Thouless, yeah, we initialize, say, our problem here somewhere for some fixed gamma, yeah, and then the RG flow, yeah, here is a critical point. The RG flow below the critical point, it goes down and finds this line of fixed points here. This is where the nonlinearity, this nonlinearity is irrelevant. Yeah? It flows to 0. This is lambda. So this means when the nonlinearity is irrelevant, it means that we end up basically in this simple Gaussian but gapless theory. Yeah? So then we can forget about this guy. Conversely, if we are above, so this is the direction of the flow, we reach a gapless phase. Gaussian action. Conversely, if we are above, so there exists a point, just a second, yeah, then this is the flow, yeah, and that is well known, yeah, so from Kosterlitz Thouless theory, that this is a massive phase, or gapped. And in these variables that we're looking here, I mean, you can see the cosine becomes, the coefficient of the cosine grows, yeah, even if we initialize it small. That means that the strength of this cosine potential, yeah, becomes bigger and bigger. So we start maybe like that. The coefficient becomes bigger, and the system really settles down in this minima, and it becomes confining, yeah, and at some point the strength is so big that you can linearize around one of these minima on each position in space, and that really looks like a big gap or stiffness against excitation. So this is this massive phase of this Kosterlitz Thouless problem. Now, no. I mean, first of all, I mean this RG procedure is only well defined. I mean, when we flow to 0. Yeah? So here somehow you have to view this as kind of, this tells you, the theory tells its own breakdown. Yeah. Right, yeah. The K is something that is here, or I think it's 1 over K, yeah, on this axis. Yeah, so these are the two axes. Yeah? So that has kind of, I mean, if you pull this all through, but that's the physics. Yeah? Right, at small gamma, yeah, but I think it's better, it's more intuitive in these variables. Maybe this is K or 1 over K, I think it's 1 over K. But it's clear that, I mean, it must have to do with this gamma over J. So weak measurement, the nonlinearity is irrelevant, we end up in a gapless phase. Strong measurement, gapped phase. Yeah? And that is really totally in line, yeah, with what I've shown you already numerically, so that there's really an emergent Kosterlitz Thouless behavior in this problem. U1 phase rotations. Yeah? Because I mean the original fermions, yeah, measurement operators, that's a beautiful U1 phase rotation symmetry, and that's really particle number conservation, and that's actually also a nice way to appreciate this Luttinger liquid that's popping up. Yeah? So it's essentially the hydrodynamics, if you like, of the density fluctuations of a one-dimensional system. That is why this problem is gapless in the absence of the measurements. Yeah? And what we find here, that kind of there's a window of opportunity where the problem remains gapless despite we measure it. And this gapless phase, I mean, it smells like it's a critical phase, as you can also see, and that's the reason for this log entanglement growth. Yeah? So it's a kind of, there is no scale in the problem that cuts off the logarithmic growth of the entanglement. And the basics, it's actually a very crucial point, yeah? The presence of this U1 symmetry for, I mean, the whole analysis of this problem. Okay, let's now, I mean, last thing, I mean, I walk you just graphically through it. Don't be, they come now very, very nasty formulas, but I just give you the impression, pictorial impression, forget the gray blocks, just look at the pictures, how we can go to a Keldysh path integral, because I think that completes a bit the picture of this lecture. Okay, so what we now want to do, we want to be more bold, and we want to look at n replicas. Yeah? The reason is that, as I will show, if we want to compute something like entanglement entropy, we need arbitrary number of replicas. Yeah? So therefore, let's look for a systematic construction of n replicas. So now we come really from our Keldysh language. At time 0, yeah, we have a density matrix, a pure state in this case, and we subject it to this measurement generator here, so which is just the exponentiated version of a small time step, as we had it before. Only difference, now these measurement operators here depend a little bit on the state, and there is this explicit element of noise. But we can, of course, do the evolution on 2 time strings, yeah, because we're evolving a density matrix, as in the first lecture. Now I represent the x-axis. Yes? This is now time runs out, x goes down. Yeah? So this is my spatial system, which is a line. Yeah? So on each position in the system, we have now an evolution sorting out on each position in time. If we look at a single replica, we do the standard Keldysh construction, and we average over the noise. I symbolize this with I'm connecting these 2 contours together, yeah? Because the same noise, yeah, acts on both contours. Yeah? So this is a real variable, so that acts on exactly the same on both contours. So if we average a single replica, then this is pictorially this. And what we get out without the detailed formulas is the Lindblad action for a decoherence dephasing process. Yeah? Therefore, let's look now at n replicas. But we can do this in, we want now to represent rho, trace rho times rho times rho, yeah, n times. And that is graphically what stands up there. Each of these replicas evolves in time. And then the multiplication of 2, yeah, is just gluing these boundaries here together. Yeah? But now, in this replicated formalism, the noise acts on all replicas in the exact same way. Yeah? So we not only get connections intra-replica, but also inter-replica. Yeah? So we get all these couplings, and that is precisely the effect, this fun effect of additional terms that add to the Lindblad evolution, which give this cooling effect. Okay, and right. And after everything has been said and done, yeah, I think this here is a nice picture with which we can end. Yeah? When we have these n replicas, yeah, each of these replicas gets exactly the same noise. Yeah? But you can see that, there are better coordinates to parameterize, to describe this problem. Namely, we go to Fourier space, to replica Fourier space, if you like. So we do here, there is a funny winner takes it all effect. Yeah? Namely, one of these modes, yeah, because the noise acts on all replicas in the same way, the average coordinate over all replicas gets eventually all the noise, while there's n-1 replicas which do not see the noise at all. Yeah? And therefore, also here for n replicas, we see that one mode heats up to infinity, while n-1 modes cool down to 0. So these are noiseless. And the next observation is that if you want to compute the entanglement entropy, yeah, so that is just this replicated density matrix with specific boundary conditions to connect the density matrix with respect to each other, then really only these noiseless modes contribute to this entanglement entropy. And if you then compute it, you find indeed the gapless regime, the gapless regime of this problem, so where the measurement nonlinearity is irrelevant. This shows exactly this logarithmic divergence of the entanglement entropy, while in this phase here, where the problem becomes massive, yeah, the entanglement saturates and we get just an area law. So I think with this, I'm almost already over time, and I thank you again for your attention. they are, I mean, decoupled on the level of this Gaussian approximation. Yeah? And I mean, that's actually a very valid question. Yeah? So I mean, but I mean, for this n equals 2, yeah, we have explicitly seen, I mean, that these nonlinearities, they are irrelevant. Yeah? So actually for larger n, yeah, so that's actually a kind of, I mean, we looked at a little bit larger n, but there's always this structure that is an irrelevant perturbation. Yeah. Yeah.
In the model with the left derivative,
Mm-hmm.
so one of the observables we were tracking was the cosine of phi.
Mm-hmm.
And we had our model had a left field parameter of 1. We started with 3 fermions.
Yeah. Mm-hmm.
Had we started with interacting fermions
Mm-hmm.
so that the observable we were tracking
Mm-hmm.
was relevant, for example,
Mm-hmm.
how would the results differ?
Yeah, it's a very good question. I mean, so if you want a high-level physics answer to this question, I have the feeling, and we also starting to see this in numerics, that whenever you don't break the integrability of the Hamiltonian, for example, you add something like that, interactions, the simplest interactions that are allowed for fermions, something like that. Yeah, so that is long wavelengths irrelevant, and that preserves the integrability of this model. Or I mean, in a discrete language, it would be NL plus 1. Yeah, so that goes to this long wavelength. So then we preserve this log law. Yeah? Statement number 1. I think what is really an important point to see this log law is indeed that the system doesn't want to thermalize, because this volume law, I view this quite globally, I think it's a possible point of view, as a thermalization in a microcanonical ensemble, because, I mean, you will occupy generic states in Hilbert space in a non-integrable dynamics, and those are generic states in Hilbert space are always volume entangled. Yeah? While here, I mean, the mechanism I presented is precisely such, yeah, so that we really cool down to a single state, yeah, under this non-Hermitian dynamics, and that's really these problems here with integrable Hamiltonians, they are much closer, from my view, to quantum phase transitions, while these volume to area law transitions, I would compare them to classical phase transitions, yeah, in the sense that they end up in a highly entangled and generic, and I mean, it's equivalent to a mixed ensemble state. Yeah. Yeah.
So does it make sense to talk about some measurement conditions like the CIFA, so when
Very good question. Yeah, I mean, I think indeed that's something that I.
it applies to the form.
Yeah. No, I think that there is a pretty interesting connection, yeah, so which we are also exploring, but let me maybe put it like that. So I give you 2 pictures. So let's take a Hilbert space, and say here is a corner of Hilbert space with its product states, or very weakly entangled states. Yeah? Now, what this measurement dynamics will do, yeah, it will even bring you into this weakly entangled subspace. Yeah? While, I mean, now, same subspace is here, but if the Hamiltonian dominates, it will bring you definitely out of this space, yeah, of this set of spaces in states in Hilbert space, and it will bring you to the more strongly entangled states. Yeah? Now, what you can think of, yeah, so let's put here a kind of, let's single out among these possible measurement outcomes, let's single out one state, yeah, which, I mean, is a representative measurement outcome, a product state. Yeah? And let's devise the dynamics, yeah, so such that it really is directed towards this state. This is precisely, yeah, modifying the Hermitian measurement operators by a unitary correction, if you like, into something that has a direction in Hilbert space. Yeah? And this is indeed something, yeah, so where you can get rid of this configuration entropy that we generate by the randomness of the measurement outcomes, and really speak about one representative wave function, which kind of becomes observable if we find the way to take out the configuration entropy of the measurement randoms. I think that was now, I can tell you in private, but there is definitely an interesting, maybe more high level, there's an interesting analogy between these measurement-induced phase transitions and what is known as absorbing state phase transitions, yeah? Which are really phase transitions which either collapse into a single state or do not. Yeah? And this phase transition from an absorbing state to a non-absorbing state, and there's a very close parallel to these measurement-induced phase transitions. Okay, that was maybe more confusing than helpful, but would also take more time.